We're going to practice question set number 11 that you guys worked on yesterday. Question number 1 says, the following diagram shows 2 point sources and selected field lines. We have a positive, we have a negative. We've seen this before, but we've seen these field lines, these solid lines before. These are electric field lines. So solid field lines result from determining the direction of the net electric force acting on a test charge placed at a point on the line. In other words, they're electric field lines, right? They're electric field lines. Now, what about these dashed lines? They result from connecting those points on a plane that have the same electric potential when a test charge is placed at that point. We've never really talked about that. Electric potential we have a little bit, the energy per coulomb of charge, but these lines that join the equal potential, like we haven't really talked about that. So how are we supposed to answer this? The field represented by the solid lines is a vector scalar. The field represented by the dashed lines is a vector scalar. The solid lines are a little bit easier because we know that an electric field, and that's what we have with the solid lines, is electric field lines, it is most definitely a vector field. So that's a bit easier. We can remember that one. But what about the next one? What about these dotted lines? These, sometimes we call them equipotential lines that we haven't even really seen. How do we know whether they're vector fields or scalar fields? You don't have to know anything about these lines other than that they don't have arrows. Therefore, they are scalar fields. If it needs a direction, that direction is going to be represented by an arrow. And we have no direction represented by an arrow, so they must be scalar fields. You don't make it harder than it has to be. I think when you look at that, it's like, oh yeah, of course. But sometimes we struggle a little bit with trying to overanalyze that question. Numeric response number 1. The electric field strength at a distance of 4 centimeters from this point charge is what? Let's draw this out. Here's my point charge. I'm trying to find the field strength 4 centimeters away from it. First of all, the field will point away from the positive, right? This positive that we know something about, its charge 1.2 times 10 to the minus 5. That can't possibly be experiencing the field right there because it's not there. Therefore, it must be it's not an experiencer, it's a producer, right? So let's use the producer equation. E is equal to kq over r squared. We know k, we know q. We just got to make sure that we make r 0.04 meters and then square that. When we do that, it works out to be 6.74 times 10 to the 7, or 6747. If this was b times 10 to the w, it would be 6.74. A, B, C, D, it would be 6747. Two, the field between the top and the bottom grids of the system. Is this a uniform or a non-uniform? This would be uniform. First of all, let's determine the direction. The direction is towards the bottom. How do you know that? Well, you know that because I just told you, but how did I know that? Yeah, if I've got a positive test particle in there, which way would it go? It would be repelled by the top and attracted to the bottom. It would move to the bottom. The electric field always goes away from the positive toward the negative. Okay, so it points downward. Now we want to find a field here. This is a uniform field, so we're going to use those bottom 2 equations. The one that's going to work for us is this one, E is equal to delta V over delta D, the producer equation, the uniform producer equation. The potential difference here is 1200 volts divided by 4 meters, which gives me, what is that, 300? No, 30. 30 volts per meter. So we're going to say our answer is, oh wait, I don't even see volts per meter. Yeah, same thing. 30 newtons per coulomb, and we already said that it was down, so the answer would be B for that one. There's a couple of hard questions on here. 3 is getting a little trickier. Pair of parallel plates. Parallel plates, what kind of field? Uniform field, right? Last 2 equations in that Venn diagram. Separated by a distance of 1 centimeter, connected to a 12-volt battery. The magnitude of the electric field is E. Second parallel plates, 3 centimeters, 6-volt battery, which describes E2 in terms of E1. I don't know about you, but to me, this one kind of comes down to variable value changing. Anybody think that? I said E1 is KQ over R squared. Sorry, I said it's delta V over delta D. I used the wrong producer equation there, right? Parallel plates, I should use my uniform producer equation, not my non-uniform producer equation. Okay, so there's E1. E2 is going to be equal to, well, the potential difference is half of what it was. Yeah. And the distance is 3 times what it was. Is that right? So it's going to be 1/6 that, and that we know is the original, so it's going to be 1/6 of the original electric field. How many people did it that way? How many people actually calculated the electric field of both of them and then divided them? That's fine. That's fine. I like this. I don't even know that I like this better. It's just the first one that came to my mind, that's all. It's probably about the same amount of work-ish, right? 4, really like this one. This is a tough one, I think. How many people said A for this one? B? C? D? So there's like 5 people that said A, somebody that said B, and then everybody else is afraid to take a stand and tell me what they said, what they got. Let's draw a big positive right here. Blue positive. Let's make this a big negative green. Negative 16. We know the answer is not going to be B or C. Here's why. The field caused by the blue at point 2 and number 3 is away from the blue. The field caused by the green is which way? Toward the green. You can't have a net field of 0 when these two fields point in the same direction. They have to be equal magnitude, opposite direction in order to cancel and give you a net field of 0. So it can't be position 2 or position 3. Good? Okay, let's take a look at position 4. We're kind of guessing here now, right? Position 4. The field caused by the blue one is which way? Don't tell me left or right, toward or away. Michael? Away, which is to the right. What about the green one? It's toward or away? Toward. Why am I drawing that green one so much bigger? For 2 reasons. 2 reasons. What's one of them? Yeah. It's closer. Okay, closer distance means a stronger field. Okay, what's the other reason? That's the main reason, by the way. Yep. The charge. Charge is bigger. So it's closer, bigger field, bigger charge, bigger field. Are those two going to cancel out and give me a net field of 0? No. So the answer must be 1. Those of you said A must be correct. But let's just double check that, okay? The field caused by the blue here is away from the blue. The field caused by the green is toward the green. How do I know they're the same length? The charge, green charge is 16 times the charge of blue, right? Doesn't that make for a bigger field? Yep. But it's 4 times the distance. And if you square 4, you get, right. So because of the charge, it's 16 times greater field. Because of the distance, it's 16 times smaller field, which means it's the same field. So we're going to say if those are the same, then they would cancel each other, and the net electric field would be 0. Good. Now, how many people said that one? Less. And now more hands are going up. People that were afraid to speak up before, afraid to be. Don't be afraid to be wrong. Just take a stand. Tell me what you got. It's okay to be wrong. You wouldn't have been wrong there. Anyways. Okay, number 5. 2 parallel metal plates are this far apart. This potential difference, what's the force? What's the force on this? Pretty straightforward. This is a uniform field, so those last 2 equations in the Venn diagram, the bottom 2 equations, we're going to say E is equal to F over Q, or F is equal to Q times E. Multiply those together. Make sure you make that in meters. Oh, wait. Oh, it's not quite as easy as I thought, actually. Not quite as easy as I thought. What's E? We don't know, right? Charge is 3.2 times 10 to the minus 19. Remember, we're allowed to use either of those bottom two equations because it's a uniform field. Gives us a value of 5.3 times negative 15. How many people got that one? Okay, good. Well, here's a good one. Oh. Hey, wait a second. This is your first real graphing question on a quiz, right? Well, this isn't even really a quiz, but it's a practice quiz. Just saying. Potential difference versus plate separation for parallel plates. The rate of change of potential difference with respect to plate separation. What is that? What are we really asking for? The rate of change of y-axis with respect to the rate of change of the x-axis. What are we really looking for? One word. Slope, right? We're looking for the slope. Slope is rise over run. Pick 2 points on the line. Okay, it doesn't really matter where they are. Pick 2 points on the line. When I do that, I should get, well, in this case, I would get, what, 21 minus 0 over 10 minus 0, which is 2.1. Oh, wait, what did I forget to do? What did I forget to do that I tell you guys to always do for other graphs, but this one too? Ed? Yeah, check your units. Check your units, 10 to the minus 2. So 2.1 times 10 to the minus. Oh man. Kidding me? So that becomes 21 then, right? 2.1? 2.1? What is it? What? 21 times 10 to the minus 2 divided by 10 times 10 to the minus 3 is just 21, isn't it? Is that right? Anybody? D? Yeah. Okay. Okay. Whew. Cross over yet? The proper units for the slope of this line, proper units would be volts per meter, right? Y-axis over x-axis. So we have 21 and volts per meter. The physical quantity that the slope represents, this is a good one. First time we've had to do this on a quiz or something like this, right? Done it a couple times on lab activities. What does the slope mean? How do you go about doing this? In your labs, 2 of them, we said y is equal to mx plus b. How come? Straight line graph, right? Straight line. The y-axis is, they used to, this is an old question. It's 2007, they switched our curriculum up like 12 years ago. Prior to that, we still had a lot of the same stuff in it, including potential difference, but the symbol they used to use for potential difference was V. Now they use delta V, which is better because it's difference, right? So the symbol they use now is better. If this was a current question, they would have actually wrote delta V there on my y-axis. Good? All right, so what's my y-axis? Delta V. What's M stand for? Does this ring a bell? What's M stand for? Not for this graph, right? But we've done this for other graphs. What's M stand for? Slope. What's X? That would be the distance between the plates. Plate separation, they now call that delta D, not just D. What's the y-intercept there? Well, pretty close to 0 if it's not 0, right? So delta V is equal to the slope times delta D. Now we come up with an equation from our data sheet. E is equal to delta V over delta D, and we rearrange it to solve for the same variable. Make it look as much as possible like what you see over there. And then we start crossing things off. Delta V because it appears in both. Delta D because it appears in both. What am I left with? The slope is equal to E, the electric field. The answer for this is C, the field strength. And finally, number 9. There's a good question too. Man, so many good questions on this. The electric field strength that is just sufficient to suspend a proton in the Earth's gravitational field near the Earth's surface. What? What does suspend mean? Float? Yeah. Okay, float, not move. If something's not moving, if something's suspended, if something's floating, it's in a state of, starts with an E, equilibrium. It's in a state of equilibrium. Remember that word? It's in a state of equilibrium. If it's in a state of equilibrium, then that means the forces must, yes, equal, cancel. I'm thinking starts with a B. Balance, yeah. Forces cancel, balance, equal, whatever. Okay, all means the same thing. So forces balance. So we're going to say this force equals this force. Well, what forces balance? Two forces balance, but what forces balance? Yeah. Yeah. So the electric force and the gravitational force. The word suspend means balance, equilibrium. Two forces have to be equal. You just have to figure out which two forces they are. Don't set the fields equal to each other. Fields will never be equal. Forces, if it's suspended, yeah. Gravitational force is m times g. What's the electric force? KQ1, Q2 over r squared? Possibly. That doesn't seem very helpful. E is equal to F over Q. The experiencer equation seems more helpful. F is equal to Q times E, and we solve for E. Oh, here we go. So M, my mass here is mass of proton, 1.67. Times 9.81 times the charge. Gives us a value of 1.02 times 10⁻⁷ meters per coulomb.